this set of notes, we're going to continue looking at multivariate probability distributions. So previously we looked at joint distributions and marginal distributions. Now we're going to introduce the idea of conditional distributions. And so it ends up that we can use the joint probability distribution and the marginal distributions to help us find conditional distributions. So we have an example here to illustrate this. And the first thing we need to do is we're going to find the marginal distribution for both x and for y. So we're going to start out with the marginal for x. And we know that x is greater than or equal to 0. So looking at the marginal of x, to find f of x, what we are going to do is we are going to integrate over the sample space of y. Well, notice that if we look at y here, y is restricted between 0 and x. So since y is restricted between 0 and x, when we integrate over y, we're going to integrate from 0 to x. And this is going to give us the following. So then our marginal for x is as follows. All right, next we need to find the marginal for y. And again, notice here that y, if we don't consider x, is anywhere greater than or equal to 0. So if we want to find the marginal for x, the marginal for y, we're going to integrate over the sample space of x. Well, notice when we consider y, x, the smallest it can be, is equal to y. So we're going to integrate from y to infinity, e to the negative x dx. And I'll let you confirm on your own that that is equal to e to the negative y. So the marginal of y is as follows. Now using this, we can find conditional distributions, or conditional probabilities. So notice in this case, we're interested in the probability that x is less than 1/2, given that y is less than 1/4. So recall what we know about conditional probabilities. We know that the probability of A given B is equal to the probability of A and B divided by the probability of B. So notice when we think of our distributions, really what we have here is in the numerator we have the joint, and in the denominator we have a marginal probability. So notice that this probability is equal to the probability that x is less than 1/2, y is less than 1/4, divided by the probability that y is less than 1/4. So what we can do is we can use the joint distribution to find the numerator and the marginal distribution to find the denominator. So looking at our numerator, we'll have the following. And so again, notice this is coming from the joint distribution. And then in the denominator, if we look at the marginal of y, we would have the following. And then from here, we could perform that integration to find the actual values. Next, we're going to talk about the idea of independence. So recall that two events A and B are independent if and only if the intersection is equal to the probability of A times the probability of B. Well, we could do something similar. So consider this right here. And one thing to note is that the comma means the same thing as and. Okay. Well, this implies the following. Alright, so using what we know about independence, what we can say here is if we look at capital F of AB, we know that's equal to the probability that x is less than or equal to A and y is less than or equal to B. So if x and y are independent, then that probability must be equal to the probability of x less than or equal to A multiplied by the probability of, oops, and that should be a y, not an x there, less than or equal to B for all possible values A and B that we could come up with. And so that's actually going to give us here our definition of independence. And so notice we could then write this for either the discrete case or the continuous case. And then of course if x and y are not independent, then we say that they are dependent. So let's look at an example here. So the question is, are these independent? Well, if you'll remember, we actually already found the marginal for both x and y for this example. And so just to remember, here we have that the marginal for x was equal to x plus 1/2. And then the marginal for y was equal to y plus 3/2 y squared. And so what we can do is we can look at that product. So we have the marginal of x times the marginal of y is equal to the following. And that is obviously not equal to f of xy that we have up at the top of the page. Therefore, we know that x and y are dependent. So we have a theorem that can help us out when determining if two random variables are independent. And it says the following. Suppose that f of xy is strictly greater than 0 if and only if we have an x that lies between a and b and a y that lies between c and d for some values a, b, c, and d, then x and y are independent random variables if and only if f of xy is equal to g of x times h of y, where g of x is a non-negative function of x alone and h of y is a non-negative function of y alone. And notice here, those values of a, b, c, and d can either be positive or negative infinity if need be. And so our question here is, can we use Theorem 5.5 to determine if x and y are independent? And remember, we already know that they're not. So, but can we do that? So notice we see that f of xy is greater than 0 for 0 or x between 0 and 1. And for y between 0 and 1. So i.e. what we could do is we could say let a equal c equal 0 and b equal d equal 1. And then we have that f of xy is equal to 2xy plus 3/2 y squared, Well, notice this is equal to y times 2x plus 3/2 y. So notice we can't seem to factor f of xy into a function of x and a function of y. But just because we can't do that doesn't prove that they can't be factored. So the theorem actually doesn't help us in this case. So this theorem is helpful when we want to use it to prove two things are independent. It's not helpful if we want to show that two things are dependent. So we want to keep that in mind. So here at the bottom, I'm actually going to use a little bit of space on the very last page there. We're just going to look at one other example. So let's see an example where this could help us. So consider this distribution. All right, so first, notice that we can see that f of xy is greater than 0 when x is between 0 and 1, and y is between 0 and 1. So just like before, we're going to let a equal c equal 0 and b equal d equal 1. Well, notice that f of xy, we can write that as 6x squared times y. So if we let g of x be equal to 6x squared and h of y be equal to y, then by the theorem, they are independent. So here's an example where we can use the theorem to help us prove independence.